Welcome back in another lesson about fuel cell. So in the last lesson we have focused our attention mainly on the descriptions of conventional types of fuel cell. And so we have described the working principle, the main characteristics, pros and cons of a proton exchange membrane fuel cell, an alkaline anionic exchange membrane fuel cell, and a direct methanol fuel cell. So we have defined basically which types of fuels are used, the structures of the electrodes, the structures of the electrolyte composition. And now what we can do is focusing our attention on another class of fuel cell. The fuel cell working at high temperature. So now we are going to speak about high temperature fuel cell. But why high temperature? Because in this case the operating conditions require high temperature. Reasons for which we can avoid the system for water management, extremely important for instance in conventional fuel cell, as in the case of proton exchange 1, in which basically the amount of water should be tuned in order to avoid the drying of the membrane. But in this case, since we are using completely different types of electrolyte, not real membrane but solid electrolyte often, we are able to avoid this water management control. And in general, the characteristics typical of a high temperature fuel cell are really promising, even if also in this case we have some problems. So now let's start with the descriptions at the very beginning of the first types of high temperature fuel cell. So the first types of high temperature fuel cell that they want to describe is the solid oxide fuel cell. So SOFC, solid oxide fuel cell. These types of fuel cell is based on use as electrolyte with the use of a solid oxide as electrolyte, or maybe a ceramic material. So here, no non-wetted membrane, proton exchange membranes are used, but a ceramic material and inorganic oxide is used as electrolyte in order to veiculate ions able to close the circuit. So basically, in according with this technology, we can have different pros and different cons. For instance, the advantages are a quite high efficiency, a long-term stability, quite interesting fuel flexibility. This is probably one of the most important aspects considering the possibility to use directly carbon monoxide together with hydrogen. And this literally means that we can proceed with an internal reforming directly in the anode, or maybe also introduce fuel gas as basically source of fuel. But we will see basically these aspects in a moment, but the fuel flexibility is probably one of the most interesting aspects considering these types of technology. But we have even a relatively low cost, and we have a pure gas emission. So it's basically a green process. It's not complete a green process, since obviously we have some release of species has carbon dioxide. We know that carbon dioxide is not toxic, but it's also true that there are a lot of important environmental problems concerning the amount of carbon dioxide in the atmosphere. So even if we have a pure gas emission, it's also true that this is not a complete green process. So, but we have a lot of advantages connected with this technology, the solid oxide fuel cell. But together with these advantages, we even have some problems. And these problems are respectively, since we are working at high temperature, a temperature range between 800 Celsius degree and 1000 Celsius degree, in order to ensure the working principle, we need to achieve this temperature, and this required time. So we have long start up time. It requires a little amount of time in order to reach this temperature and then proceed with the workings of this battery, of this fuel cell. And another problem concerns in the temperature that leads to some mechanical and chemical compatibility problems. So we can have some problems considering the fact that since we are working at high temperature in presence of chemicals, we need to select specific types of materials in order to improve the life of these cells without observed breaking down of its structure and so on. So obviously when we are working at high temperature, we need to be aware on the mechanical properties of our materials that we are used for building this cell. And these types of problems is extremely more important, for instance, in another types of high temperature fuel cell, not the solid oxide, but the molten carbonate fuel cell, in which the high corrosive environment is responsible for breaking down the component of the cell. But we will see these concepts speaking about molten carbonate fuel cell in a moment. So now focusing our attention on the solid oxide fuel cell. We have described the positive aspect, so the high efficiency, the fuel flexibility, the pure emission, the relatively low cost, the quite long stability and long-term stability, but even the problems concerning the mechanical and chemical compatibility problems, and also this is probably the most characteristic types of problem concerning more or less all the high temperature fuel cell, the long start-up time. So, but from a practical point of view, which is the structure and the compositions of the materials used in this fuel cell? So, the fuel cell, the solid oxide fuel cell, can tolerate different types of fuel. And so the fuel, it could be or hydrogen again, or the gas form, or carbon monoxide. This is quite interesting advantages, because we know that often the hydrogen is a result of the steam reforming process that can create carbon monoxide and hydrogen. So a steam reforming leading to the generations of syngas. So what does it mean? That since both this species and this species can be used as fuel, we can introduce directly the syngas inside our cell, our anode. And basically, this is really interesting because we can feed directly with syngas our anode, or maybe we can use them directly, exploiting the high temperature of these systems, internal steam reforming directly inside anode. And avoiding also problem concerning the poisoning of the catalyst since we are working at very high temperature. But I need to define all these concepts after I've designed the structure of this cell. So we have our anode, our negative electrode, we have our solid oxide or ceramic materials, the electrolyte, and we have our cathode. Okay, so these materials, so first the semi-reactions associated with these types of cell are during the discharging. Even if we need to remember that often we need to say that when we are dealing with fuel cell, we're not dealing with something that should be recharged, or better, it should be recharged only by introducing more fuel. And so since we are able to introduce fuel continuously inside our cell, we are able to recharge it, but it's not a real recharge, it's not a conventional recharge as in the case of lithium-ion batteries, for instance, or lead acid batteries and so on. So basically this is just charging involving the use of new fresh fuel introduced continuously in line in our cell. So in this case we have that at the anode we have the reaction between hydrogen, if our fuel is hydrogen in the gas form, together with oxygen 2 minus, migrating from this electrode to the surface of this electrode. We will see how it's possible to ensure the migration of these reduced oxygen atoms as oxygen 2 minus in order to have the oxidation and so the generations of water and 2 electrons. Obviously, these types of reactions can involve even the presence of carbon monoxide. So we can even have the generations of carbon monoxide interacting with this, and now the product is not water anymore, but is carbon dioxide, and again we have 2 electrons. So we can have this oxidation or these oxidations, or if you're using syngas, both of them, or maybe also if you're using some hydrogen that is impure, we can have even the conversions of CO, because in this case, since we are working at high temperature between this range and this value, the absorption energy of this species on the catalyst is reduced, and so we have no poisoning problems, both concerning CO2 and also concerning carbon monoxide. And this is another extremely interesting aspect of these types of technologies. We have no catalyst poisoning since we are working at high temperature. So now, from a practical point of view, we can say that the materials on which these types of anode is composed, obviously here we can have the water elimination or the carbon dioxide elimination as a product of the oxidation with the release of electrons. So this material is composed of nanoparticles of nickel mixed together with this material that is yttria stabilized zirconia. So we are looking at a zirconium oxide, zirconia, in which yttrium oxide is used in order to stabilize a specific structure, allowing, together with nickel, the possibility to ensure a certain conductivity, a certain porous structure, and at the same time a catalyst place in which the oxidation reactions can occur. So the electrode is composed with nickel particles, nickel nanoparticles in a porous matrix of yttria stabilized zirconium. Why these types of species? Why is yttria stabilized zirconia? Because yttria stabilized zirconia is also the composition of our electrolyte. Our oxide, our solid ceramic materials, our solid electrolyte is composed of yttria stabilized zirconia. And so here we have yttria stabilized zirconia plus nickel, just because in this way we are able to ensure the conductivity, a porous structure allowing the passage of hydrogen, and at the same time, the fact that this electrode is made of the same materials partially of this electrolyte ensure a good compatibility between it and the electrolyte itself. And yttrium stabilized zirconia is used because it's able to vehiculate these reduced oxygen atom from the cathode to the anode. But now, since we have described basically the compositions of the anode, the compositions of the electrolyte, and the reactions involved in the anode, we need to understand what is happening on the cathode. So on the cathode, we have an electrode that is composed of lanthanum, strontium, and manganite. This is a specific particular material that is able to catalyze the oxygen reduction reaction, and is useful since we have a good compatibility between these yttria stabilized zirconia. But it's important to say that the lanthanum, strontium, manganite is active in order to promote the oxygen reduction reaction only when we are working on a temperature that is higher than this one. And this is the reason for which the temperature is so huge. Because if we want to promote the oxygen reaction reduction, that is this one, so from molecular oxygen collected from the atmosphere in a conventional gas diffusion electrode, together we are able to promote the formations of these reduced species. Yes, okay, this is reduced, sorry. So, plus 2 electrons in order to give this species. So if we want to promote this reaction, we need to use lanthanum strontium manganite and working at this temperature. So what's happening is that these reductions occur, we have the generation of this species that can migrate in the yttria-stabilized zirconia. So this is stay for yttria-stabilized zirconia, and this is stay for lanthanum strontium manganite. What is happening is that from this lanthanum strontium manganite cathode, these atoms are able to migrate in the yttria-stabilized zirconias and reach the catalyst surface on the anode, and we can have the oxidations of hydrogens or carbon monoxide. So basically this is the working principle of a solid oxide fuel cell. But what is important is that the capability to work at this temperature is able to ensure also the fact that we have no poisoning, and we can even exploit this high temperature in order to promote the steam reforming baby or a reforming of lighter fraction directly in the anode. So what we can do is use this temperature in order to generate directly in situ our hydrogen or our fuel in general. And this is extremely important. This is one of the most important advantages. For instance, we will see in a moment how also in molten carbonate fuel cell we can exploit this internal reforming in order to use more energetic dense gas in order to produce hydrogen as the further fuel. And so this represents one of the most important advantages connected with these types of materials, even if there are some problems concerning the start time and so the time necessary in order to reach this temperature. But basically we have defined all the main aspects of a solid oxide fuel cell. Okay, now we can proceed and we can start speaking about another types of extremely interesting high temperature fuel cell, and this second high temperature fuel cell is the molten carbonate fuel cell. Moment. So molten carbonate fuel cell. Molten carbonate fuel cell. So a molten carbonate fuel cell is an high temperature for a cell working in a temperature value that is higher than 600 Celsius degree. In this case, basically we are exploiting the use of a molten carbonate salt as electrolyte that is impregnated, that is filling a solid matrix composed as beta aluminum. So we have a beta aluminum solid electrolyte that is completely saturated with a molten carbonate salt. And this ensures basically the working principle of our fuel cell. And also in this case, we can exploit the use of different types of fuel, and we can even, and since we are working at high temperature, the poisoning effect due to the presence of carbon monoxide or carbon dioxide are really limited. And so basically, also in this case, we can describe a system, an electrical device, sharing the same types of advantages of a solid oxide fuel cell. But in this case, since we are dealing with the presence of carbonate at this high temperature, we are dealing with a quite aggressive and corrosive environment. And this is the reason for which we need to be aware on what types of materials should be used in order to build this cell. And this is also the reason for which, in general, the long life, the long-term stability of this cell is not as important as in the case of solid oxide fuel cell. And this is one of the only type of advantages that is not shared because in this case the lifetime is significantly reduced with respect to solid oxide fuel cell due to the high corrosive environment created with these types of electrolyte. So also in this case, basically, we can define a structure that is quite similar with respect to the one previously seen. So we have our anode, our cathode, the anode, external circuit, the solid electrolyte. In this case, the solid electrolyte is a beta aluminum solid electrolyte, the same saturated with molten carbonate salt, plus, for instance, molten sodium carbonate or potassium carbonate, and so on. So we can have different types of salt, potassium carbonate, sodium carbonate that are completely molten due to the high working temperature. Sorry. And then we have this beta aluminum solid electrolyte. That is a surrounding material adding these types of formula, obviously in an overload crystal lattice. This is basically just in order to highlight the ratio between the atoms present in the beta aluminum solid electrolyte impregnated with these types of salt in a molten state. Then we have our anode. The anode is often composed as nickel, but is not only nickel. In this case, is nickel in an alloy. Is nickel in an alloy containing also chromium and aluminum. Why? Because in this way we can avoid the sinterings of our electrode, obviously in a porous structure in order to allow the diffusions of fuel. But this is an alloy with respect, for instance, the yttria stabilized zirconium with nanoparticles of nickel-based anode in the solid oxide fuel cell. In this case we have a real alloy. And the cathode, from the other hand, is not composed as lanthanum, strontium, manganite, but in this case is composed with lithiated nickel oxide. What does it mean? It's a nickel oxide in which lithium it was intercalated. And in this type of electrode, the cathode, is important to say that the contact between the electrolyte, the carbonates, and its can promote the dissolution of this nickel oxide, releasing nickel inside the electrolyte. But we know that the nickel can ensure and increase the electrical conductivity, and we can even reach problems concerning short-circuiting condition. So it's important to be aware of this. And in general, basically now we have defined what is. So we have defined what is the structure of the anode, the material used for what concerns the buildings of the cathode, and also what does it mean a base electrolyte and a molten carbonate salt. But now it's important to look at which types of reactions are involved here. So the very beginning is important to say that one important step that is always present often in these types of molten carbonate fuel cell is the fact that we can fill, due to the high temperature, this type of cell with hydrogen. But this hydrogen, it could be converted in hydrogen directly inside the anode. So basically what it means is that we can fill methane, and in a process known as internal reforming, so an internal reforming, we can convert methanol, that is extremely interesting because it's high energetic dense gas, is higher with respect to hydrogen, that increase the energetic density of our device, And so we can use methanol and react involving the use of this high temperature together with steam in a steam reforming, promoting the formations of carbon dioxide and a lot of hydrogen. And so we can charge a more energetic density gas directly in the anode, and due to an internal reforming we can promote the formations of hydrogen. And in this situation we can use this hydrogen on the negative pole, on the anode, already created. So we have the temperature that can promote the formations of this species, and this species is directly used as a fuel in a further moment and can react together with the carbonate anion migrating inside the base electrolyte from the cathode. We will see the connected reaction. So basically something similar with respect to the sodium oxide fuel cell, but in this case we have not the migrations of oxygen 2-, but we have the migrations of these carbonate anions inside the saturated base electrolyte. And we have, so the reaction, promoting the formations of 4 times carbon dioxide, 4 of water, and 8 electrons. And this is what's happening inside anode. And in the cathode side, from the other hand, we have that this carbon dioxide is taken and it can react as always with these electrons together with oxygen, with the formation of these carbonates that can migrate inside the base electrolyte and reach the anode. So we have the reaction between oxygen, so it's an oxygen reduction again, but these are reductions involving the use of carbon dioxide and the electrons collected from the external circuit, released due to the product of the oxidation. And we have in this way the formations of carbonate that can migrate in the base electrolyte and reach these types of anode, promoting the formation of electricity. So here we can have that water and the CO2 are released. Here we have our well-known diffusions of oxygen, and at the same time also carbon dioxide are introduced in order to ensure the reductions of oxygen and promote the formations of this species that can migrate and close the circuit. So basically these types of characteristics are all the most important characteristics of a molten carbonate fuel cell. Now what we can describe is the last types of high temperature fuel cell. It is quite different because it's a high temperature fuel cell that is involved basically the use of phosphoric acid. So the phosphoric acid fuel cell, phosphoric acid fuel cell. So the phosphoric acid, phosphoric acid fuel cell is a type of fuel cell that is working in a quite reduced temperature with respect, for instance, solid oxide fuel cell and molten carbonate fuel cell. Here the temperature is significantly reduced, so is between 150 Celsius degree up to 210. So basically we can say that in this case the temperature, even if it's quite higher with respect to conventional types of fuel cell, a proton exchange membrane fuel cell, in which we know that the temperature should remain 100 Celsius degrees, or better even 180 Celsius degrees in order to avoid the drying. In this case, since we're using phosphoric acid as electrolyte, we are not pure or highly concentrated, we do not have a huge water management systems because the temperature, the working conditions are higher, but not so higher as the molten carbonate fuel cell and in the solid oxide fuel cell. So in this case, the working principle is quite close to the working principle of proton exchange membrane fuel cell. So phosphoric acid fuel cell is behaving quite close with respect to proton exchange membrane fuel cell, but is composed in a different way. We have our cell in which the two electrodes are made of carbonate matter graphite on which platinum particles are deposited. So we have platinum on a carbon support both here and both here, with the connected problem associated with the fact that the platinum is extremely good for the oxidations of hydrogen, but not so good in order to promote the reductions of oxygen. And so we have the problem concerning the overtension. With these types of situations is well described in the specific video concerning the descriptions of the proton exchange membrane fuel cell. So we have the cathode, we have our external circuit, and we have an electrolyte. In this case, the electrolyte is composed of phosphoric acid, pure or really concentrated, in a silicon carbide solid matrix. So basically what is important in this case is that the reactions involved are basically the same of a conventional proton exchange membrane fuel cell, because on the anode we have the reduction, the oxidation, of hydrogen that can promote the formation of H+ and electrons. So electrons are collected from the external circuit and can reach the cathode, whereas H+ are released on the base, and we have at this temperature, the temperature range of these types of cell, a quite high ionic conductivity, and so this H+ can migrate from this anode and reach the surface of the cathode, remembering that the electrical conductivity is extremely small, and so this is important in order to avoid short circuiting and allow the passage of electrons only towards the external circuit. So in this case, we can say that when electrons and protons can reach the cathode on the surface of this platinum catalyst, we have the oxygen that together with electrons and together with these protons, it can react in order to promote the formation of water. So here we have that hydrogen is filled. This is a gas diffusion electrode in which oxygen is taken from atmosphere, and again we have the remotion of water here. So nothing different. What is interesting is that in this situation the water released as a product, since we are working at high temperature, it can be instantaneously converted in steam. And since we know that the efficiency of phosphoric acid fuel cell is around 40 or even smaller, not as in the case of solid oxide or molten carbonate fuel cell, in which the efficiency can even reach 60%. Here is smaller, but due to the fact that we can take advantage of this steam, we can use this steam in order to move a steam-driven turbine, and so we can increase our efficiency of the overall process from 40% up to 70%, and we can increase a lot the final efficiency. Remembering also that we respect conventional proton exchange membrane fuel cell, since we are working at a high temperature, we can use even a certain amount of hydrogen in which we have some impurities, because this high temperature protects platinum from the poisoning from carbon dioxide and even from the poisoning of carbon monoxide when the amount of carbon monoxide is not higher than 1.5% in the source fuel. And so this means that with the use of these types of cell, the first commercialized, the phosphoric acid fuel cell, we are able to extend the different types of fuel that can be used as starting source for generations of electricity.